There are stars in the universe, so faint, so slow, so cold, that they challenge everything we understand about stellar physics. Stars that shine only a little brighter than the cosmic background itself. Stars whose temperature barely rises above the freezing emptiness of space. Stars that should not exist because every model of thermodynamics, every equation of stellar structure, every rule of gravitational collapse insists that such objects cannot remain stable. Yet they do. They endure, silent, frozen, suspended somewhere between life and death. These are the cold stars, the paradoxes of the deep cosmos. And their existence forces us to reconsider what a star actually is. A star, the classical sense, is a machine of heat. Gravity squeezes matter inward, and that compression produces temperature, and temperature produces fusion, and fusion creates pressure, and pressure holds gravity at bay. It is a delicate balance, a constant struggle between collapse and expansion. But cold stars break the balance. They follow another logic, a hidden logic, a logic we do not yet know how to describe. Imagine an object only a few degrees above absolute zero, and yet it keeps its shape. It does not collapse into a black hole. It does not evaporate into a faint cloud of dust. It simply remains. For this to happen, the matter inside must behave in ways completely unfamiliar to ordinary physics. Some researchers suggest that the atoms in such a star lose almost all thermal motion. They become trapped, locked, like particles inside a crystallized vacuum. Matter without heat, matter stripped of almost all internal energy. A star whose interior is not a blazing plasma, but a vast, silent structure where movement has nearly stopped. There is a theory called degenerate thermal collapse. It suggests that at extremely low temperatures and extremely high densities, matter can enter a special regime where it no longer behaves as individual atoms, but as a single, unified quantum system. In such a state, the star does not require heat for stability. Its structure is supported instead by quantum pressure, a strange kind of resistance to compression that arises not from temperature, but from the fundamental behavior of particles. This pressure, unlike thermal pressure, does not weaken as the star cools. It remains steady, unyielding, and so A star can become cold, very cold, almost completely cold, yet still remain a star. Another hypothesis goes further. It proposes the presence of exotic particles, particles beyond the standard model, that could stabilize matter at temperatures close to zero. These particles are sometimes called cryons, hypothetical, discovered, but mathematically possible. A cryon-rich star would lose heat faster than it could create it. Every spark of energy would be drained away, consumed, redirected into an invisible channel. The star would cool again and again until its temperature reached a point at which normal physics would predict collapse. But collapse would not occur because the exotic particles inside would create an inner lattice, a framework, a skeleton of quantum structure that resists gravitational pressure. The star would freeze, but remain intact. There is also the frozen core theory. According to this idea, the center of a cold star becomes so low in energy that its atoms no longer vibrate. They do not fuse. They do not break apart. They do not interact in the typical ways. They simply stay in place, as if locked inside a cosmic crystal. Such a core would be astonishingly stable, harder than diamond, denser than any known metal, a region where time itself seems to slow down. Around this frozen heart, the remaining layers of the star continue to cool until the entire object settles near the temperature limit of space. A star that has almost stopped being a star. But if a star becomes this cold, why doesn't it heat itself again? Gravity should compress it. Compression should create heat. Heat should restore activity. Yet none of that happens. One explanation is the presence of dark cooling channels. Imagine that the star loses energy, not through ordinary radiation, but through invisible forms of emission. Dark photons, action like particles, neutrino-driven thermal leaks. These channels would drain heat with enormous efficiency, far faster than gravity could regenerate it. It would be like trying to warm a room while all its windows are fully open. No matter how much energy is produced inside, it is carried away instantly. The star never rises in temperature. It stays cold. Another possibility involves gravitational extraction. Some extreme astrophysical environments can pull energy out of matter in ways we barely understand. Nearby massive objects, primordial black holes, ancient cosmic filaments, or unknown gravitational anomalies may siphon off thermal energy, as if feeding on the star's interior. This would leave behind a stellar remnant, gradually drained of all warmth, a dim ember cooling endlessly, never returning to heat. And there the consequences. A cold star creates a region around itself that behaves unlike any ordinary stellar system. Its surroundings fall into a cold trap. Temperatures drop. Dust motion slows. Gas clouds stop glowing. Everything become quiet, still, suspended. Planets orbit differently as well, because when a star cools, its internal structure changes, and with that, its effective gravitational field can shift. Planets move as if the star is slightly less massive than measurements suggest. This produces odd orbits, delayed rotations, unexpected tilts, a system that seems frozen in time. In the darkest regions of the cosmos, there may exist entire dead systems, solar systems, where every world is cold, every movement is slow, every trace of heat has long since escaped. Silent constellations orbiting a star that barely glows, a star that whispers instead of shines, a star that defies the laws of physics simply by continuing to exist. A cold star is not merely an astronomical curiosity. It is a challenge, a defiance, a violation of what we assume to be the fundamental behavior of matter. Because when we look at such an object, we are forced to confront a single uncomfortable truth. Heat is not guaranteed. Fusion is not guaranteed. Stellar life is not guaranteed. There are deeper forces at work, forces that can cancel heat, slow time, lock atoms into immobility, erase the energy that should naturally arise from compression. And when these forces dominate, a new kind of star appears, a star that refuses to glow, refuses to burn, refuses to follow the rules. Some astronomers believe that cold stars are remnants, ancient relics, survivors of an era when the universe itself was cooler, denser, and filled with exotic conditions. To them, these objects are fossils, pieces of the early cosmos that drifted into the present almost unchanged. But others argue the opposite. They believe cold stars are not old. They are new, formed under extreme environmental circumstances, in regions where dark matter concentrations or gravitational anomalies prevent stars from heating during collapse. In these zones, a protostar would never ignite, never reach fusion, never become luminous. It would simply compress, cool, and stabilize as a dark, frozen sphere, a star that never had a chance to shine. This leads to another possibility. Cold stars may be transition objects, intermediate stages between white dwarfs and something more exotic, long after a typical star dies. Its remnant cools slowly, millions of years, billions of years. It radiates away the last traces of heat, eventually becoming a black dwarf, a star that no longer emits visible light, a corpse of stellar evolution. Yet theoretical models predict that true black dwarfs should not exist yet. The universe is not old, Duff. But what if some stars can skip the line? What if exotic cooling channels accelerate the process? Then cold stars may be glimpses of the far future, objects we should not yet be able to observe. And yet, here they are. Another strange effect arises near these stars. The space around them seems unusually calm. In typical stellar environments, gas is heated, dust glows faintly, magnetic fields twist and ripple. But near a cold star, nothing stirs, nothing brightens, nothing moves quickly. It is as though the star extends its stillness outward, a bubble of slowed thermal activity. Some call these regions thermal shadows. Others describe them as zones of entropy suppression. Whatever the name, their existence implies that the star is not merely cold, it is actively cooling its surroundings, de-influencing space itself. This raises a disturbing question. Where does the lost heat go? Energy cannot vanish. It must move somewhere. If a cold star drains energy continuously, efficiently, without releasing it in normal forms of radiation, then something somewhere is absorbing that energy. This something might be a field, a particle, a hidden dimension, or an unknown sector of physics that interacts with ordinary matter only through temperature and gravity. A dark thermal reservoir, a sink for heat, a place where energy flows, but from which it never returns. If such reservoirs exist, the universe may have more than one, entire networks of invisible channels through which stars lose energy. This would mean that cold stars are not isolated anomalies. They are warnings, indicators that the cosmos has hidden structures, silent conduits, pathways for lost heat. And if these pathways grow or intensify, they could one day influence whole regions of the universe. Galaxies cooling faster than expected, clusters dimming prematurely, cosmic evolution slowing down, a quieting of the cosmos, a gradual fade. There is also the question of motion. Cold stars do not behave like typical stars in their orbits. Their trajectories can be strange, subtle, delayed, misaligned. This happens because a star's internal temperature affects its mass distribution, its internal pressure, its compactness. As the star cools, its radius shrinks, its core stiffens, its gravity profile changes. Planets orbit slightly differently, as though the central mass has shifted or decreased or migrated inward. Cycles become longer, ellipses become distorted, seasons change unpredictably. A cold star system feels artificial, engineered, as if someone or something turned down the heat. Some exoplanets detected near extremely faint stars show unusual behaviors. Frozen oceans without reflective glare. Atmospheres that don't move. Locked rotations far more stable than expected, as though the entire system has been put into a kind of cosmic refrigeration, a suspended animation of physical slowdown, pause, deep in the void, far from galaxies. Cold stars may drift in silence, their light nearly non-existent, their heat barely measurable. To detect them, we would need instruments capable of sensing the faintest possible infrared whispers, barely above the background glow of space. Even then, many would remain invisible. Black giants, frozen suns, quantum remnants, hidden spheres of almost perfect stillness. And yet, despite their invisibility, their influence may be vast. A cold star that moves near a gas cloud can cool it dramatically. A cold star that drifts through a stellar nursery can alter the formation of new stars by removing heat from the region. A cold star entering a young system can destabilize it without emitting a single photon. Its presence is a gravity, well, wrapped in thermal silence, a quiet force, a ghost of stellar physics, a star that radiates cold instead of heat. Wes, look deeper. The consequences of cold stars unfold. The surrounding space responds. Gas clouds cool. Dust slows. Magnetic activity diminishes. Entire stellar neighborhoods can be influenced by the presence of one frozen giant. And planets, their orbits are subtly shifted trajectories that should follow simple Newtonian rules become strange. Elliptical paths stretch, cycles stretch, spins synchronize unnaturally. The star itself appears almost indifferent, a frozen sphere, quiet, motionless, and yet it is not dead. It is alive in a different sense. Its existence speaks of physics that we barely comprehend. A star that communicates not with light, but with absence, with silence, with the slow, deliberate extraction of energy. Some theorists imagine that these stars might be feeding a hidden cosmic network, a system of energy channels that span beyond ordinary detection. Channels where heat is drawn away and disappears from our measurable universe. If true, cold stars are not anomalies. They are signposts, indications of hidden physics, deep processes that shape the cosmos silently, the frozen core inside. The exotic particles, the dark radiation channels, all converge to produce a new category of stellar object, an object that challenges intuition and forces us to rethink the very definition of a star. Around these objects, life as we understand it would be impossible. Systems would age slowly. Formation of new stars may be inhibited. Dynamics of matter reduced, frozen, suspended, yet in their stillness, cold stars offer insight. They hint at the ultimate fate of matter, the far future of galaxies, and the eventual cooling of the universe itself. They also push us to imagine the existence of particles, forces, or dimensions that are invisible, but real channels that extract energy silently, without trace. To study a cold star, we must observe not what it emits, but what removes. Not the light, but the absence of heat. Not the activity, but the frozen calm around it. Detection is difficult. Infrared telescopes may barely sense them. Gravitational effects may offer hints. Subtle shifts in orbital paths. Unexpected cooling of nearby matter. Each observation is a window into something deeper, something that links thermodynamics, quantum physics, and the hidden structure of space-time. Cold stars may also be ancient relics, survivors of early cosmic epochs, formed in usual conditions, where temperature, density, and dark matter were extreme. Or they may be new phenomena, created in special pockets of space, where heat is removed faster than it can form, where fusion never ignites, and the star remains a silent, frozen orb. Either way, the existence of cold stars expands the frontier of astrophysics. It challenges our understanding of what is possible, and it reminds us that the universe is stranger than we imagine. As our instruments improve, we may detect more of these objects, mapping their distribution, understanding their interactions, and learning the mechanisms that maintain their frozen state. Perhaps one day, cold stars will reveal secrets of matter, of energy, and of cosmic evolution. Oh, then they remain silent witnesses, frozen giants in the vast cosmic sea, quietly shaping space and time around them, teaching patience and humility to those who seek to understand. The end. The story of cold stars is a story of limits and of exceptions, of matter in extreme conditions, of forces that act beyond light and heat. Oh, the universe reminding us that not all is as we perceive, and in their stillness, in their quiet persistence, we find a profound message. The cosmos is vast. The rules are not absolute, and reality is far more complex than we can yet measure or imagine. Cold stars endure, and through their endurance, they expand the boundaries of human knowledge. The universe is not uniform. It stretches, it flows, it swirls, but in some regions, there exist colossal, inexplicable barriers. They are sometimes called cosmic walls, structures that rise like invisible cliffs across vast stretches of space. Their nature is mysterious. Are they made of matter, of energy, of something more abstract? A defect in space itself? Some scientists suggest that these walls are the remnants of early universe phase transitions. During the first fractions of a second, the cosmos underwent radical changes. Fields condensed, symmetries broke, energy froze into new configurations, and in this process, thin, energetic membranes may have formed, stretching across millions of light years, like invisible cheats. Other theories propose that cosmic walls are ultra-dense layers of space, unlike ordinary matter or gas. These layers have a density extreme enough to influence light and matter without being directly observable. Imagine a region of space so compressed, so peculiar, that it bends trajectories, slows approaching objects, and absorbs signals. Some researchers compare these walls to topological seams, boundaries between regions, where the structure of space differs subtly, where cosmic domains meet, like the junctions of tectonic plates, but on a universal scale. These walls may not be stationary. They may drift, shift, respond to the motion of galaxies, or to the expansion of the universe itself. Light behaves strangely near them. A beam traveling through a normal galaxy cluster follows predictable paths, but approaching a cosmic wall, the light seems to bend unusually. It slides along the surface, twists, its speed appears to change relative to nearby reference points. Objects approaching the wall may decelerate subtly, as if the fabric of space itself resists their motion. Signals, such as radio waves, sometimes vanish near these structures, disappearing without absorption, without reflection. It is as though the walls exist in a realm beyond our usual perception. Some cosmic walls are linked to large-scale filament structures, galaxy clusters, superclusters, and voids, all organize around these invisible boundaries. They create compartments, cells, bubbles, where matter evolves differently. Some cosmologists suggest that we ourselves may reside inside one of these gigantic cells, a vast region of space bounded by cosmic walls that defines the local geometry of our observable universe. If true, our view of cosmic expansion and of galactic motion may be subtly influenced by these walls. They may define the limits of cosmic flows, the paths along which galaxies cluster, the orientation of filaments. They may be remnants of a larger multiverse, the boundaries of our bubble, colliding with adjacent bubbles, leaving traces in the form of these colossal walls. If so, each wall may carry information about regions of space beyond our perception, regions of different ages, different expansion histories, different physical constants. This sense, cosmic walls are not merely structures. They are archives, memory, traces of the universe itself. Yet we only the effects, not the walls directly. Distorted light, slowed matter, anomalous signals, and these subtle clues allow astronomers to map them, even though the walls remain invisible. The physics at play may involve exotic fields, fields that interact weakly with ordinary matter, fields that store energy in unusual forms, fields that resist detection, yet influence everything around them. The very existence of cosmic walls suggests that space is not a uniform void, that the early universe was patchy, dynamic, layered, and these layers persist, silent, invisible, but real. The interaction of cosmic walls with light and matter is subtle yet profound. Light passing near a wall does not simply bend. It slides, it stretches, it may even vanish temporarily. Astronomers detect these effects by tracking distant quasars, gamma ray bursts, other luminous objects when a signal disappears or deviates without any visible obstruction. A wall may be the cause. Objects moving toward the wall experience unexpected deceleration, not from friction, not from gravity, but from the space itself resisting motion. Radio waves, pulses, and other periodic signals sometimes fade when near a wall. This produces what some call anomalous radio gaps. It is as if the wall creates a vacuum, not of matter, but of interaction, a domain where ordinary physics is altered, just slightly enough to produce measurable effects. Some cosmologists suggest that cosmic walls act as boundaries of multiverse bubbles, each bubble a region where physical constants, laws of physics, and cosmic history differ subtly. Collisions between these bubbles may leave scars, giant walls, invisible but vast. These boundaries may also preserve memory of the collision itself, the way energy and matter were redistributed, the shifts in cosmic expansion, the relative ages of regions. A wall may represent a phase transition, frozen in place, its thickness minute in relative terms, but stretching across millions, even billions of light years. Galaxies approaching these walls often follow distorted paths. Clusters may align along their edges. Filaments may bend. Voids may appear larger or differently shaped. Cosmic walls are not necessarily permanent. They may drift, stretch, shift under the pressure of expansion or the gravitational influence of nearby superclusters. Yet, despite their motion, they leave traces, the patterns of galactic distribution, the anisotropy of large-scale structure, the subtle lensing of distant light, all point to their presence. Some theorists speculate that these walls could explain anomalies in the cosmic microwave background, regions of unexpected temperature variation, or unusual polarization may result from past interactions with invisible barriers. Others propose that walls affect the expansion rate locally. Space may stretch faster or slower, depending on the density and distribution of nearby walls. If we exist inside a cosmic cell, our local universe may appear isotropic, but globally, it is divided by immense, invisible partitions. These partitions define flows. They define clusters. They may even regulate the formation of massive structures. In this sense, cosmic walls are both actors and archivists. They store the history of the universe while simultaneously shaping its present. And yet, their physical composition remains elusive. They ultra-dense membranes, exotic fields, a subtle curvature of space-time, or something entirely unknown beyond our current understanding. Each observation, each distortion of light, each delayed signal adds a small piece to the puzzle. Over time, we may map these walls, begin to understand their role in cosmic evolution. But for now, they remain among the universe's greatest mysteries. Silent giants, invisible cliffs, boundaries of the known and the unknown beyond their immediate effects. Cosmic walls raise profound cosmological questions. Why do they exist? Are they remnants of early universe events or ongoing phenomena? One hypothesis suggests that walls mark boundaries of multiverse bubbles. Imagine the universe not as a single uniform expanse, but as a patchwork of regions, each born under slightly different conditions. Where these regions meet, walls form, invisible, yet stretching for billions of light years. Collisions of bubbles. During the first moments after the Big Bang, could have left these immense structures behind. Some walls may be ancient, older than any galaxy cluster, older than most stars, preserving the memory of cosmic phase transitions. Others may be younger, formed from more recent interactions, where large-scale flows of matter, energy currents, have sculpted the fabric of space. Inside these walls, matter organizes differently. Galaxies align along their edges. Clusters form chains and filaments. Voids open where density is reduced. Light passing nearby distorted. Signals may vanish. Paths deviate. Subtle effects, yet measurable. Some theorists suggest we may live inside a cosmic cell, bounded by walls we cannot directly observe. Our universe is more compartmentalized than it seems. Our observations may be influenced by unseen partitions. Cosmic walls may also carry information about other regions regions beyond our observable horizon. Each wall may encode the age, the density, the expansion rate, the domain it separates. Perhaps they hint at variations in physical constants, differences in fundamental laws between one cosmic bubble and another. Their very existence challenges assumptions. The universe is not perfectly homogeneous. It is stratified, layered, structured on the largest scales. Walls may define flows of matter. They may regulate formation of clusters. They may influence the rate of cosmic expansion locally. Yet, despite their size, their presence is subtle, detected only through deviations, through gaps in signals, through strange alignments of galaxies. The physics of cosmic walls may involve exotic energy fields, all dense space membranes, or topological defects frozen into the structure of space-time. Some may act as semi-permeable barriers, allowing light and matter to pass, but only partially, altering trajectories, damping motion, creating anomalies in the cosmic web. Other walls may be more rigid, impenetrable barriers, isolating one domain from another. The study of these walls requires patience, precision, a new kind of observational strategy. Telescopes, radio arrays, gravitational lensing surveys, all combined to detect their subtle influence. Cosmic walls remain among the universe's most enigmatic features. They connect astrophysics, cosmology, the physics of the very early universe. They remind us that the cosmos is not uniform. It is layered, complex, full of structures we can barely perceive. Yet, in these invisible partitions lies information, clues to the formation of galaxies, to the dynamics of superclusters, to the hidden history of space itself. As we map them, we gain insight into the grand architecture of everything around us, and perhaps we will one day understand how these silent, colossal walls have guided the evolution of the universe from the earliest moments to the vast expanse we observe today. Cosmic walls endure, hidden yet present, shaping space and matter while preserving the memory of the universe, more complex and stranger than we can yet imagine. In their stillness, they tell a story of beginnings, of boundaries, of a cosmos that is not uniform, but divided, layered, and alive in ways we are only beginning to understand. The universe, as we perceive it, is only a fragment of reality. We exist with 3 spatial dimensions and 1 of time. Yet, according to M theory, there are more, many more, 11 dimensions, hidden, compact, curled up, on scales too small to see. Most of these dimensions are microscopic, invisible to ordinary instruments. Yet their presence shapes everything. The strength of forces, the behavior of matter, the motion of stars, all subtly influenced by dimensions beyond our perception. Gravity, for example, is weak, much weaker than electromagnetism or nuclear forces. Some physicists suggest this is because gravity can leak into extra dimensions. A force spread thin across 11 dimensions, felt faintly within our 3-dimensional brain. Our universe may be a 3-dimensional membrane floating like a soap film in a higher dimensional space. The cosmic stage is not a simple 3D arena. It is a vast, multi-dimensional expanse where entire universes exist on sheets moving in relation to one another. These sheets, or brains, may drift, collide, and influence each other. Imagine 2 giant membranes gliding through higher dimensional space. Occasionally, they meet, they interact, and energy is released. Some theorists even propose that the Big Bang was such a collision, 2 brains crashing together, sparking the creation of our universe. The concept of brains expands the notion of what a universe can be. Each brain a world unto itself, with its own stars, its own galaxies, its own dimensions of space and time. In some models, our universe may periodically approach other brains. The theory is sometimes called ekplanation, or brain proximity theory. This interaction could explain otherwise mysterious phenomena in cosmology. Gravity, again, offers hints of hidden dimensions, since it is not confined entirely to our brain. We perceive it as weak yet subtle deviations in gravitational measurements may be evidence of its multidimensional leakage. Some suggest the elusive dark matter may be an artifact of nearby brains, gravitational influence from universes we cannot see, manifesting in our own dark energy too. Might be a footprint of extra-dimensional geometry, a push, a tension between sheets of space stretching the cosmos without any visible source. The geometry of 11 dimensions is not arbitrary. It constrains particle physics, defines force strengths, and sets the stage for cosmic evolution. If M theory is correct, then every particle, every photon, every gravitational ripple is subtly influenced by the hidden architecture beyond our senses, brains, collisions, extra-dimensional fluxes. These are not just speculation. They offer explanations for phenomena that our ordinary three-dimensional universe cannot fully account for. And yet, most of this reality remains imperceptible, hidden beyond our instruments, waiting for new ways to observe. The study of M theory demands imagination and mathematical sophistication. It asks us to visualize dimensions we cannot see, interacting in ways we cannot directly measure. But hints exist: gravitational waves, in anomalies, in cosmic expansion, in subtle patterns of galactic motion. Each signal, each deviation may be a whisper from another brain, a glimpse into a universe beyond the one we know. The notion that reality is multidimensional is profound. It transforms our understanding of matter, space, and time, tells us that the universe is far richer and stranger than our daily experience suggests. The M theory universe is a stage with 11 dimensions, the vast ensemble of brains and membranes interacting in ways we are only beginning to grasp. The brains, these vast sheets of space, are not mere abstractions. They are physical objects, albeit in higher dimensional space. Imagine a sheet so thin, yet stretching across billions of light years, floating in a realm beyond 3 dimensions. On its surface, a universe forms. Galaxies, stars, planets, even life merges, all constrained to the brain. Other brains exist nearby, sometimes distant, sometimes closer. When brains approach each other, forces may arise. Tidal tresses, energy transfers, ripples across the sheets, collisions, rare but dramatic, could release massive energy, potentially giving birth to an entirely new universe. Some cosmologists hypothesize that the Big Bang itself was such a collision, two brains crashing together in higher dimensional space, sparking energy and matter, creating the cosmos we inhabit. Between brains, there may exist gravitational bridges, tunnels through higher dimensions, linking universes. Gravity, like electromagnetism or the strong nuclear force, is not bound to a single brain. It can seep into adjacent dimensions, allowing a weak but pervasive influence. This leakage explains why gravity is weaker than other fundamental forces, and it hints at phenomena we observe but cannot explain. For example, dark matter may be the shadow of mass in a neighboring brain, a gravitational echo without visible matter. Similarly, dark energy might reflect tensions between brains, a push, a stretching arising from higher dimensional interactions. The geometry of the extra dimensions affects particle physics. It determines how forces behave, how particles acquire mass, how interactions unfold. The arrangement of brains, the curvature of extra dimensions may even influence the expansion rate of the universe. Gravity, therefore, becomes a window into the higher dimensional structure. Subtle anomalies in planetary orbits, slight deviations in galactic motion, unexpected patterns in cosmic microwave background radiation may all be footprints of neighboring brains. Some theorists speculate that collisions between brains could recur, periodic interactions bringing bursts of energy. Could these events explain periodic phenomena in our universe? Cosmic rays, gamma ray bursts, fast radio bursts. Perhaps they are whispers from the multidimensional realm, echoing across our three-dimensional brain. The mathematics of M theory allows for 11 dimensions, 7 of them compactified, hidden, curled in on themselves. The remaining 4 are the familiar 3 of space and 1 of time. Yet these hidden dimensions determine the behavior of matter and energy. They constrain possibilities. They define constants. They shape evolution. Every particle, every force, every ripple in space-time may carry information from beyond the observable universe, our three-dimensional world, a membrane floating in a richer cosmos, a cosmos filled with brains, interacting, sometimes colliding, sometimes drifting apart, yet always influencing each other. The notion transforms how we think about space, time, and reality itself. The M theory universe is not just a backdrop for stars and galaxies. It is an active, dynamic, multidimensional arena, one where universes collide, forces leak across dimensions, and gravity serves as a bridge to unseen worlds. It suggests that every anomaly we observe may be a signal, of realities beyond our perception. Gravity is our window into the higher dimensional cosmos. Unlike the strong or electromagnetic forces, gravity is not confined. It spreads, it leaks into hidden dimensions beyond our three-dimensional brain. This explains its relative weakness compared to other forces, yet its subtle influence reveals the shape and structure of the multi-dimensional universe. The concept of gravitational bridges emerges. Tunnels linking brains, channels through higher dimensions, through which energy or particles may travel. Some anomalies in galactic rotation curves may not be due solely to dark matter. They could be footprints of neighboring brains, their gravitational influence casting shadows on our universe. Dark energy might also be interpreted as the tension between brains, a stretching of space as membranes move relative to one another. Such multi-dimensional dynamics could manifest as subtle variations in expansion rates, in gravitational waves, even in the distribution of matter. NEM theory also suggests that our universe is not isolated. Other universes may exist on parallel brains, nearby but hidden collisions or near encounters could inject energy, trigger new structure formation, or leave lasting imprints on the cosmic microwave background. The extra dimensions, 7 of them, compactified, control particle interactions, determine constants of nature, shape the evolution of galaxies, and influence star formation. Mathematically, these dimensions are intricate, curled into Calabi-Yau shapes, complex geometries, tiny but powerful, encoding the physics of reality. Our three-dimensional perception is like a shadow of a richer, multi-dimensional existence. We move along our brain, limited in sight, while a vast, unseen architecture lies in parallel through precise measurements of gravity, of high-energy particles, of cosmic structures. We may glimpse the hidden scaffolding of the universe, every gravitational anomaly, every unexplained acceleration, every subtle lensing of light could carry a message from higher dimensions. Brains may collide, and in their interactions, birth universes, they may pass close to each other, disturbing space and energy without any direct contact. The implications are staggering. Our universe, just one membrane among many, each influencing, each interacting in ways we are only beginning to theorize. Theory transforms our understanding of reality. It suggests that space is far richer. Matter is shaped by hidden dimensions, and gravity, not merely a force, but a messenger from the unseen. The cosmos is multidimensional, layered, complex, and vast beyond comprehension. Our universe, our brain, exists in a delicate balance, floating in a sea of higher dimensional space. Collisions may have sparked creation. Gravity may be a bridge, and dark matter and energy, clues to worlds beyond perception. This framework, the Big Bang, may be a collision, but also a window, a glimpse into the dynamics of reality beyond our senses. The study of M theory reminds us that what we see is only a small fraction of what exists. Reality extends across 11 dimensions, woven together in a structure both elegant and mysterious. The universe, as we know it, is but a membrane floating among countless others, a single surface in an endless, multidimensional expanse. Our understanding is growing slowly with every observation, with every theoretical advance, bringing us closer to the true fape of all reality. Theory is not just mathematics. It is a story of dimensions unseen, forces unfelt, and a cosmos far more complex than human eyes alone could ever perceive.